Hello and welcome once again to the Maths Jedi channel. This is another of my A-level series. This is the final video now in the Logarithms chapter. So this is going to revise through some exam type questions for natural logarithms and logarithms, talk about the laws a little bit. We'll go through some of the stuff that we've met in the previous videos. So if you're new to the channel, please do have a look at those. And of course, I'm always going to say leave a like. That would be really helpful and would help support the channel a ton. So, just going through some questions here on mixed exercise 14. That is at the end of the chapter, so you can find your way to that. I would encourage you to do the whole of this exercise. I'm not going to do the whole of the exercise in this video, but I will do a fair amount of the questions. The page reference, as you can see, is page 334. So all of these questions can be found inside of the textbook, and I would encourage you to work your way through these in your own time. To start with then, we're going to do a couple of questions just to get familiar with some of the concepts that we've discussed in previous videos, just to make sure we've got ourselves understanding what's going on. So I'm going to choose my pencil here and just talk about one or two questions. So let's just make our way through some of these early questions, particularly question 3. Let's just talk about those because that's kind of a basic sort of idea of how logarithms work. So in the question it says, given that p is log q 16, so let's just write that out for a little bit because I want to talk through again just how logarithms are defined, make sure you've really got a good understanding of how logarithms are done. So remember that this is the base, so q is the base, this is the power, and this is the outcome. So this is the base, this is the power, this is the outcome. So what this is really saying is that q to the power p is equal to 16, okay? So q to the power p is 16. So that's what we're being told in the question. So the first question, part A, is saying what is log to the base q of 2? Now it'd be quite useful to relate these two things together, so 16 and 2, and how they're related. So we know that 16 is 2 to the power 4. So I can rewrite this up here as log base q of 2 to the power 4. That's what 16 is. Now, using the rules of logs, we know that when we're raising a power here, we can bring this power down to the front. We're using one of the rules of logs, we can bring this power down to the front. It's like differentiation, but it's not the same. So we can effectively look at this as being log base q, 4 log base q of 2. So this expression up here, p log q 16 is the same as this, 4 log q2. So we know that this was p. And this would be, we know that this was p, so this would also be p. So that must mean that this here is a quarter of p, because we know that 4 lots of p, or a quarter of p, is log base q of 2. So if you rearrange that, you can see how that's the same. Similarly here, on part B, so log base q of 8q. Now again, it would be useful to write these in terms of 2. So we're going to do a couple of things here. First of all, we're going to split this off using the rules of logs. So because this is two things multiplied, I can rewrite this as log base q of 8 plus log base q of q. Using the rules of logs, that's absolutely fine. This here, log base q of q, is 1, because anything that has the same base and has that at the outcome must be 1. And then we look at log q8. Well, this is 2 cubed, so in a similar way to before. We can bring this power down to the front, so I'll do that up here. So we've got 3 log q of 2 plus 1. Now we knew earlier that log base q of 2 is a quarter p. So this is 3 lots of a quarter p. So that's 3/4 p plus 1. So that would be the answer to part B. Okay, so just using the rules of logs there, some manipulation of the rules of logs, you can see how you sort of have to sort of translate some of the stuff into logarithmic language and sort of think about the things that you did at GCSE in terms of finding common bases. But the principles are very similar. So as long as you base things down and try and think about the smallest base and writing things in terms of the smallest base that you see, you shouldn't really go wrong with these sorts of questions. I'm going to do one of these. I'll do question 4C just to give you a practice of that, but you can try the others. So it's asking you to find x here, solving the equation to 3 significant figures. The question here is 10 to the power of x equals 6 to the power of x plus 2. So very simply we take logs. So let's take logs on both sides. It doesn't matter what log base you choose, but it'd be good to choose a base that's helpful for us. So log base 10 would seem to be helpful for us here because we've got a 10 in the question. Using the rules of logs, I can bring down the x to the front here. And then similarly, sorry, I'll just cross it out. Similarly, I can do the same thing on the right hand side. So I'll do the same here. Try and make sure that x plus 2 stays as a function on its own. Now, log base 10 of 10 is 1. That's 1. So this is just going to be x on the left hand side. And then you've got x plus 2 log 6 here. We're going to multiply out the brackets. I'll take all the x expressions to the other side. And then finally take out x as common. Be a bit messy, this pen. And then we're going to divide through by 1 minus log 6 here. So I'm going to go right to the top again. I'll rub some stuff out and then I'll divide through by this expression on the left, 1 minus log of 6. So let's just grab the pen. Here we go. X equals 2 log 6 over 1 minus log 6. We're going to pull up the calculator and have a look at what this does. So here's my calculator. So again, useful because we can do it as we see it. So you can see I've used the fraction button to make that work. As with before, we're going to have to be log base 10 here. It's just to make it easy for myself. I've got some wire in the way. Just bear with me a minute. Need to move that out of the way. There we go. So log base 10 and of 6, and then underneath 1 minus log base 10 of 6, and see what that gives us. So it's 7.36, we're going to say 7.02 to 3 significant figures. So that's what x is to 3 significant figures. Okay, we're just going to check the answers. I didn't check the answers in the previous question. Let's do that real quick. So let's have a look. Oh, that's handy. So quarter p, that's the previous question. 3/4 p plus 1, there's the previous one. And then question 4, we're just going to look at part C, 7.02, you can see it there. So absolutely fine, 7.02, so no problem. Let's trash my notations. Right, let's just go down the page a little bit and pick another one. Let's have a look at a nice one. I think I've done plenty of examples like the example number 5, but you can have a look at that in your own time. So let's have a look at one of these. So because it talks about exact solutions. So let's have a look at E and F here. So I'll pull up the notepad once again. We'll look at E and F. So let's look at E first of all. So it says e to the x plus e to the minus x equals 2. So this on the face of it looks like quite a complex problem, but actually it's very simple. We need to understand what's going on the left hand side. So it's e to the x plus 1 over e to the x equals 2, because this is e to the minus x here. Many people choose to take logs here. We don't need to take logs at the moment because we want to keep things kind of as simple as we can. Taking logs makes it slightly more complicated sometimes. So we can actually manipulate this quite easily. If I multiply everything by e to the x, I would have e to the 2x here, because this is e to the x. Then I'd have 1, because this times e to the x. And then I have e to the x on the other side, 2e to the x on the other side. If I take all the e to the x expressions together, you can see now I'm getting a familiar pattern. I can let y be e to the x in a similar way to what I've done on previous videos, and you will get a nice substitutional quadratic. So let's do that. This is going to be y squared minus 2y plus 1 equals 0. That factorizes quite quickly, and you can then go from there to get your answer. Let's just do that real quick. So it will be minus 1 and minus 1. So y equals 1, e to the x equals 1, so x is 0. So that's the only solution that's going to work here, is x is 0. Looking at part F, log of 2 plus log of x equals 4. The logs help us here, so we're going to use the rules of logs. So again, because we are adding two logarithms, we can multiply these two things together. So 2x, that's one of the rules of logs that we know. We're now going to anti-log everything. So we're left with 2x on the left-hand side, but because we're doing natural logs, that's e to the 4 we're going to have over here. Just in case you're not sure what's going on here, remember this is log base e of 2x equals 4. So here's the base, there's the power, there's the outcome. So there's the base, there's the power, there's the outcome. So I call it anti-logging, but really we're just writing it out in terms of logarithms that we know. So let's go from here. So x is equal to e to the 4 over 2. We're being asked to write exact solutions, so that's why I'm leaving it as e to the 4 over 2. Let's just trash my annotations and check the answers, make sure I'm doing the right things. Don't want to leave you astray. A, E and F. There's E, so 0, and then F, e to the 4 over 2. Brilliant. Okay, I'll leave you to do question 9. It's very similar to some of the ones I did in the previous video, so I'm not going to do too much of those. Let's have a look at some of these over on the right hand side. I would like to do one sort of graphic question. Okay, so we'll do 12 and 13, I think, just because they look interesting. So I need to just get my pad up. Right, so question 12 first of all. Let's have a look at this. It's talking about different spheres. It's talking about V. Let's get my pen up. V being A s to the power b. Okay, so it says first of all, show that log v equals this. So we're going to take logs on both sides, base 10 here. Using the rules of logs, let's split this up. And then bring down the power. And you can see that's what they're asking you to show. That matches. And then copy and create a table of the values, giving your answers 2 decimal places. So you can get your calculator and plug those in. I'll let you do that. Plotting a graph of log v against log s. I'm expecting a straight line, so it's trash my annotations. I'll show you what we should be expecting. So log v against log s. So remember that's what we would expect. So it's interesting the way they've sort of done log s's first. So log v would be this axis and log s would be this axis. We're expecting a straight line, and that straight line would be crossing here at log a. So that's where the straight line would cross, and the gradient of my straight line, if I did up divided by across, would be in this case b, whatever b is, because I've got a log s axis here. So when it says use your graph to confirm that p equals 1.5, you'd need to do the triangle and do your change in y over change in x, and that should give you the 1.5. When it says estimate the value of a, you would look at where it crosses, and remember that log a is where it crosses, so whatever that value is, so I'll just assume it whatever it is, and then you'd have to do the anti-log, so a would be 10 to the power of whatever this particular value was. So whatever that value is, you need to put it 10 to the power of that to get a, and don't forget to do it to one significant figure. I'll leave you to do the detail, but that just gives you a little bit of an overview. And then 13. And then 13, we're going to do radioactive decay now. So it's talking about a substance modelled by the formula R equals, let's write the formula, R equals 140 e to the kt. Okay, where what R is a measure of radioactivity. Explain briefly why K must be negative, because it's radioactive decay. That's the answer for that. So decay means it's going downhill. So the exponential graph would look a little bit like that. Okay, so it must be when decay that it's going downhill, and so you would expect K to be negative. Sketch the graph of R against T. So again, you can do some values and draw the graph. What you would expect is a graph where, as I said, I just sketched it for you, but R is along here, T is along there, and you'd expect it to be cutting through the axis. So whereas the value you'd expect it to cut the axis, it should cut the axis at 140, because e to the power of 0 is 1. So it would cut the axis 140, but it'd be an exponential decay, something like that. It says after 30 days, the radiation is measured at 70 counts per minute. Show that K equals C log 2, stating the value of the constant C. So we've been given some values here. So let's go back to my formula again, make it a bit more squeeze at the top. Okay, so we're being told to find K, and we're being told after 30 days. So is T in days? Yes, it is. So we're going to do 140 e to the 30k, and the radiation is 70 counts per minute. So that's this. So 70. So do 70 divided by 140. That's going to be a half. So we know that e to the 30k is a half. We're going to take natural logs on both sides. So let's just do that real quick. So log of a half equals log of e to the 30k. Using the rules of logs, I can bring this power down. But because log e is 1, that effectively disappears. And I've got log of a half here. And then I can do, obviously, k is going to be on its own. To isolate k, we need to divide by 30. So it's 1/30th of log a half equals k. And then I went through this in the previous video, that log a half is the same thing as this. So it's 1/30 log 1 minus 1/30th of log 2, and that's going to be k. And then log of 1 is 0, so this bit goes away. You're left with minus the 30th of log 2. So c here would be minus 1/30. Again, you are expecting a minus number for the reasons stressed earlier. So that will give you k equals minus the 30th log 2. So c is minus a 30th. And that will give you the answer straight up. Looking at number 13, let's just stress we've got the right answer. So what was this, number 13? Let's go down. So minus the 30th, there it is. So absolutely fine, straightforward. I'll leave you to do the others. They're all good practice, this particular exercise. I would encourage you to spend some good time just going through these, making sure you've got them clicked. It might be a little while now before my next video, because I'm revising in school, so we'll be doing some work off camera. But what we'll do is I'll come back to you in a couple of weeks with the next topic, which hopefully will be just refreshing some stuff from earlier on in the A-level syllabus. In terms of today, thank you very much for watching. Bye-bye for now. Bye-bye.